Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the idealizations of high-speed compression ignition engine. Despite its simplicity, the reciprocating engine is one of the rare inventions that has proved to be very versatile and to have a wide range of applications. It is the powerhouse of the vast majority of automobiles, trucks, light aircraft, ships, and electric power generators, as well as many other devices. This is a cutaway view of an internal combustion engine, an 8-cylinder, 4-stroke internal combustion engine, and also the actual cycle in the compression ignition engine and its PV diagram. The basic components of a reciprocating engine are shown in the figure. The piston reciprocates in the cylinder between two fixed positions. The top dead center is the position of the piston when it forms the smallest volume in the cylinder. The bottom dead center is the position of the piston when it forms the largest volume in the cylinder. The distance between the TDC and the BDC is the largest distance that the piston can travel in one direction, and it is called the stroke of the engine. The diameter of the piston is called the bore. The air or air-fuel mixture is drawn into the cylinder through the intake valve. The combustion products are expelled from the cylinder through the exhaust valve. Look at these figures. The minimum volume formed in the cylinder when the piston is at TDC is called the clearance volume. The volume displaced by the piston as it moves between TDC and BDC is called the displacement volume. This is a real PV diagram from an actual ICE. The actual internal combustion engine can be idealized and modeled as a cycle with 2 heat additions and 1 heat rejection in the PV and TS diagrams. When the entire combustion process can be modeled as a combination of constant volume and constant pressure process, the ideal cycle is called the dual cycle or Sabat cycle. Now, we introduce some terminologies for reciprocating devices. The first terminology is the compression ratio. The ratio of the maximum volume formed in the cylinder to the minimum volume is called the compression ratio of the engine. The second terminology is the pressure ratio for isochoric process. It is the ratio of cylinder pressures after and before the isochoric combustion process. The third terminology is the cutoff ratio. It is the ratio of the cylinder volumes after and before the isobaric combustion process. The fourth is the temperature ratio. It is the ratio of the maximum temperature to the minimum temperature in the cylinder. The fifth is the expansion ratio. It is the ratio of the cylinder volumes after and before the isentropic expansion process. The sixth is the mean effective pressure. It is a fictitious or imaginary pressure that, if it acts on the piston during the entire power stroke, would produce the same amount of net work as that produced during the actual cycle. Now, let's talk about the efficiency for the dual cycle. When the inlet state, the compression ratio, the pressure ratio, and the cutoff ratio are all known. The dual cycle is determined. The efficiency, by definition, is. With the cold air standard assumptions we have, the temperatures can then be determined based on state 1 and the process. For the isentropic compression process, state 1 to state 2, we have this relation. For the isocaloric heat addition process, state 2 to state A, we have this relation. For the isobaric heat addition process, state A to state 3, we have this relation. For the isentropic expansion process, state 3 to state 4, we have this relation. Substituting these equations into the thermal efficiency relation and simplifying yield. This is equation 10.7. The temperature at state 4, T4, can also be determined based on the entropy differences. Checking the temperature expressions carefully, we can find that when the temperature at the end of compression is determined, the others are then determined. Okay, that's all for this task. Thank you very much, and see you next time.